So this week in the lab, we're doing the Gaussian calculations. And so this morning, I'd like to talk a little bit about what's going on under the hood in terms of Gaussian, specifically what's going on with the geometry optimization and the frequency calculation. And then also what is up with the alphabet soup that we put in to kind of pick the model. So just like your model kits, if you have a model kit and it has a certain length of bonds and a certain size of the different balls and sticks that you have, you would use that model kit to build multiple molecules, and then you could compare the sizes of those molecules and the way they look if you're using the same kit to build the same different molecules. Now, if you had different kits, it wouldn't make sense to build a molecule with one type of kit and then build a different molecule with a different kit and try to compare their sizes, right? Because the kits aren't the same. So when we talk in Gaussian, in terms of computational chemistry, we talk about model chemistries. Now, those models aren't physical. They're not balls and sticks like we had in lab, but they're mathematical models. And so the alphabet soup, like UFF or B3LYP-6-31G and so on, those are designations for the different mathematical models. And so anytime we're building molecules in Gaussian and we're going to compare them, let's say we're doing a series of reactants or something, we want to look at their reactivity, we need to use the same model for all of the species, okay? Just like we would be using the same physical models to build them and compare them, we'd use the same mathematical models to build the molecules and compare them. In our lab, though, that kind of breaks down a little bit because the models that we have aren't necessarily covering the whole periodic table. So the 6-31G with D in parentheses, that model only covers through krypton. And we want to model I2 for the iodine lab, and it's beyond krypton. And so we need to use a different model kit, mathematical model for that molecule. And so we use LANL2DZ, which covers the whole periodic table, including all the transuranic elements. So that's why we have to use that one. That's one of the answers to your discussion questions too on the lab. So a little bonus for getting here at 8 a.m. So that's why we're using the LANL2DZ for iodine and not for all of the others. Now, why don't we use that one for all of them? Well, the 6-31G is a pretty standard model, and so I wanted y'all to use that standard one with the B3LYP for all of your other calculations. So it's good to use two different models. So let's jump into the Gaussian software and discuss what's going on. So this is such a privilege. Of course, it's been around for, let's see, less than 20 years, but more than 10. So this software called GaussView. When I started, and this is like an old man, back in the day, when we started doing Gaussian calculations, it was all text. Like we had to build our molecule in a text file using a thing called a Z-matrix. And it really hampered your ability to make larger molecules. So sometimes you could get a crystallographic file for a larger molecule and convert those Cartesian coordinates into an input file for Gaussian. So that prevented you from having to go in and like type in the locations of each of the atoms. But for small molecules, we got pretty good at using a text file to build our molecules using this idea of a Z-matrix. If you want to learn about the Z-matrix, I've got a video on that for the graduate class that I teach. Now you guys have it good. You've got GaussView. So you can go in and you can pick your atoms and you can start building your molecules here in this builder window. So this is what you'll use in this week's lab. Up here at the top, if you were to select this little spot right here, let's see, you can come up here and there's a spot right here that allows you to select different elements, and you get this selection of the elements. So if you pick carbon, these are the different kinds of carbon that you can have. You see the Vesper shapes built in there. You've got sp3 type carbon, sp2 type carbon here, sp type carbon, a couple of those, and then just a carbon atom. So you can build with all the different types of carbon or nitrogen or sulfur and so on. So those are built in. So you can select the atom, you can select the type that you want to use, and then you can go back to the builder window. Now, it's nice that they have these templates, especially for the ring structures, because it's kind of a pain to build a ring an atom at a time. because when you click on the next atom, sometimes it doesn't go in a spot that's going to get you around to the ring. And so then you've got to select 4 atoms and change the dihedral to get them all lined up. So anytime you're building a ring structure, click that second little icon over there and get the rings template. And you've got like chair and boat versions of cyclohexane. You've got, heteroatom containing rings, fused rings, and so on. So this is a good tool to help you, especially when you get into something really weird like this, like you're trying to build one of these bridge structures. That'd be a real pain to do by hand. You can, but it's not very easy. And then we also have some R groups, different functional groups. These are pretty easy to build by hand, but they do have some templates. If you do those a lot, you can throw on a tert-butyl group, and then it'll be there, or carboxylic acid. Then after you've built your molecule, it's time to start a calculation. And so underneath the Calculate tab, you see Gaussian calculation setup. Now on your own PCs, if you've downloaded from Blackboard the installation files, always install the Gaussian first and then the GaussView next. So then GaussView is installed and it knows where the Gaussian program is, because the Gaussian program, G16W, it's the actual engine that does the calculations. So we want to come up here and set up a Gaussian calculation, and you get all of these options, and we'll go through these different tabs this morning. So one of the first tabs you see is this method, and this is, again, what are you actually calculating, and what kind of model are you using to calculate it. So let's go through the method tab. All of our calculations are going to be for the ground electronic state. Now this is an electronic structure software. So that's another way, we call it computational chemistry as a general category, but the specific thing that we're doing is called electronic structure. Okay, that kind of makes sense if you think about it. We're only telling it where the atoms are. And when it's drawing the molecule, it draws sticks between all the atoms. So it makes a ball and stick model, okay? But those sticks are not there. I know that your mind is like really stuck on this idea that there's 2 atoms and there's something called a bond in between those atoms. And you really are, maybe you're really stuck by thinking that there's 2 electrons in that bond, like the Lewis dot structure, okay? That's not true, okay? What's holding that molecule together is the molecular orbitals, okay? Now, how are those molecular orbitals structured? That's what this is doing. So this is calculating the molecular orbitals that hold those nuclei in their positions. So you're giving it an initial guess, and it's not a bad starting point. The Lewis dot structure, I mean, what are we doing? We did the Lewis dot structure, made the Vesper shapes, and then we're able to get the symmetries of those molecules through the flow chart. And we get the point groups, okay? Those are accurate, okay? But it's not an accurate representation of the electron cloud to think that there's 2 electrons between each atom. So we're not throwing away everything, but we are trying to like knock that idea that there's 2 electrons between each atom, or if it's a double bond, 4 electrons, kind of knock that out of your head. That's why we need programs like Gaussian. Okay. So ground state electronic calculations is what we're going to be doing. And then there's this idea of level of theory designation. So you see over here, Hartree-Fock, that's that next selection box. And then this basis set. So we're going to explore that this morning. And then down here, this charge and multiplicity. So that's a sort of getting an idea of how many unpaired electrons there are and if the molecule is charged or not. So like you did a cyanide ion. Okay, and so in that particular one, it was a -1. So here's a diatomic molecule floating around in space. Now it's hard to get it into space because it's negatively charged. It's going to be attracted to things, but still, let's say in space, right? We're looking at a dust cloud in space and we have a spectrometer on our telescope. We might see cyanide ion, okay? Because it's far enough away from any positive charges that it doesn't get sucked in. It's got enough velocity. It's just flying through space as the cyanide ion. Now, if you were to calculate that molecule in space, you'd need to tell the Gaussian that it's a -1 molecule. Now, because it has that nitrogen brings in an odd number of valence electrons. It brings in 5 valence electrons. So when we give it 1 more, now we have an even number of valence electrons. And so they're able to pair up. So everything's paired up in the cyanidine. This idea of multiplicity or spin, right here it's called spin. It's the number of unpaired electrons plus one. So this is calculation here. Now this S right here, that's the net charge or net spin. So typically if you have an unpaired electron, we would just assume that it's spin up, so it's plus 1/2. So if you take that plus 1/2 and you multiply by 2, you get 1, and then you add 1, and so then you end up with a doublet. So it would be a multiplicity of 2. But if you think about it, you got one unpaired electron, you add 1 to that, then you've got a spin of 2, or a doublet. Okay. If you have 0 unpaired electrons, so everything's all paired up, then it's the number of unpaired electrons is 0 plus 1, so it's a singlet. So the spin would be a singlet, and in all of our cases, we're dealing with singlets. The one that will trick you is, let's say you're calculating the thermodynamics of a combustion reaction. What does every combustion reaction that you've ever come across have in it? A fuel plus what? Oxygen, and makes water and CO2. Okay, so they all have oxygen, CO2, and water. Very easy to calculate on here. Then you calculate the fuel, and then you can model the thermodynamics of combustion. But the oxygen will trap you because the oxygen ground state is a triplet. So it has an even number of electrons, but at the ground state, 2 of those electrons are unpaired. That just happens to be a lower energy version of oxygen than the paired up oxygen. So singlet oxygen is higher in energy than triplet oxygen. So that would be one where you would calculate the wrong thing if you put singlet here. It's uncharged, but it would be a triplet instead of a singlet for oxygen. So that's the one place where people that haven't been paying attention would mess that up for oxygen. Okay, let's go in a little deeper on these. So these model chemistries, this is how we select the theoretical model that we're going to use to calculate our molecule. We're also going to select a basis set. Now the basis set is the mathematical functions that we use to model the flexibility of the electron cloud. So how are we going to tie those electrons to the nuclei? That's with the basis set. Okay. And then we have graphical models that we can use. We can, once we're done with the calculation and we have the electronic structure of the molecule, we can model things visually, graphically. We can model those molecular orbitals. So what we were doing in the last couple of lectures with the MOs on water, that's what we're talking about, graphical models. We modeled the water's electronic structure and then showed the molecular orbitals for each of those energy states. We could also do electron densities. We could look and sort of sum up all of those molecular orbitals into just one diagram and say, where are all the electrons in this molecule on average? So we could get a density, say, so in this particular volume, what's the probability of the electrons being in this volume, or that volume, or that volume? And if we collect all of those volumes, then we have a shape of the molecule's electron cloud. If we walk along that electron cloud with a positive charge, it's going to be attracted to areas that are negative, and it's going to be repelled by areas that are positive on the molecule. So let's say we have an acid group. If I'm walking along that edge of that electron cloud and I'm near the oxygen, it's going to be negative. But if I get over towards this acidic proton, it's pretty exposed. And so I'll see that exposed proton and it'll be positive. And so we'll see the positive and negative regions of a molecule with this potential energy surface. So those are some of the calculations that we'll learn how to do in this section. Let's talk about why we give Gaussian the locations of the nuclei, and then we let it calculate where the electrons are. The motions of the electron and the motions of the nuclei are separable because even for hydrogen, the smallest nucleus, it's 1,000 times more heavy, 1,000 times more massive than the electron. So the electron mass is 10 to the minus 31 kilograms, and the proton mass is like 10 to the minus 27. So it's more than 1,000, a factor of 1,000 in those. So I noticed this one time. I was outside and there was a bunch of cloud of gnats around me. You ever see that? You ever experience that? And you're like trying to get away from them. And so you move over here and they follow you sometimes, okay? And so you're trying to get away from the gnats, but you're so massive, the gnats don't even know you're moving. Like they're just responding. You can't move fast enough to get rid of them because they're so lightweight. And so that's the model I think of when I think of the nuclei. So even in vibration, when the atoms are vibrating apart, the electron cloud is instantaneously reacting to that. So we can completely separate the motions of the nuclei with the motions of the electron cloud. Okay, so that allows us to pick a particular geometry and calculate the electron cloud, and then move the atoms and calculate the electron cloud and see which geometry has the lowest energy. And so this is a really important tool. We can guess with our Lewis dot structure and our Vesper shapes the shape of a molecule. And we can give water, it's got 4 electron domains, 2 lone pairs and 2 bonds. And we can say that forms an electronic tetrahedral shape. We got atoms on 2 of those electron domains. And so what's the angle for an sp3 hybridized oxygen atom? What's the angle between the hydrogens? 109.5. That's an initial guess. So we would build that in Gaussian. Here's my structure of water, and the atoms are stuck there, and then we model the electron cloud, and then it's able to kind of monitor or model the forces on those atoms too by that electron cloud. So it'll move the hydrogens away from each other to relieve some of that force in the electron cloud, and then it'll model the electron cloud again and say, oh yeah, it's at a lower energy. So it'll keep expanding that angle until it goes too far, and then it'll come back, and then it'll say, all right, we're at an optimized geometry. So that's what's going on with the geometry optimization. But the Vesper shapes and angles is a good initial guess. So no matter where I move, these gnats keep following me. That's the electrons. Okay, so the nuclei are saying that. So now let's look at the energy equation. Remember Schrodinger's equation for the particle in a box. Okay, it was the Hamiltonian operating on the wave function. And it was a one-dimensional system. Okay, and we only had one particle. So we had a single electron on a wire, and it could only be on that wire. So we only had one dimension, x. But it's a three-dimensional system and multiple particles. Okay, so this is the Hamiltonian for a molecule. So H is the Hamiltonian, and it has 2 kinds of pieces to it. It has the kinetic energy piece and the potential energy piece. For our particle in a box, the potential energy was 0. So all of the V's went away, and we only had T. T and V are the kinetic energy and the potential energy. So in this molecule, any molecule, you've got nuclei that are both positive, and they repel each other. And then you've got nuclei and electrons that attract each other, and then you've got electrons that repel each other. So you've got 3 potential energy pieces, all based on Coulombic attraction. What's the distance between these 2 particles, and are they attractive or repulsive? So those are the V pieces. The kinetic energy pieces are that second derivative piece. So we take the second derivative of the wave functions. So this is the crazy thing. So we go through all of the nuclei. So alpha and beta in this are nuclei. So we have here alphas, okay? And here is the repulsion between nucleus alpha and nucleus beta, and it's 2 nested loops. So we pick, say, atom nucleus A, or 1, and then we go through 2, 3, 4, 5, 6, all the way up to the number of atoms. And we calculate the repulsion of nucleus 1 with nucleus 2 through N. Okay? And then we go to nucleus 2, and we calculate the repulsion of nucleus 2 with 3 through N. Okay? We don't do 2 with 1 again because we've already done 1 and 2, so we don't double count. Then we go to nucleus 3, and then we calculate the repulsion of nucleus 3 to nucleus 4 through N. And so this is great for computers. I mean, we would die trying to do this by hand. Okay, so we throw this into a computer with the basis set, and it can calculate the repulsion of all the nuclei. It can also take the second derivative. This is what this upside down delta is. It's the second derivative of the nuclear wave functions. Okay, and these are the masses of the nuclei. So it says the mass of nucleus 1, the second derivative of the wave function for nucleus 1, the mass of nucleus 2, and the second derivative of that mass, and so on. Then we have the electrons. So all of the electrons have the same mass, and we just go through electron 1, 2, 3, 4, 5, 6, and calculate the second derivative of the electron wave function in all space. So this is also r, theta, and phi. So theta and phi are kind of like longitude and latitude around a sphere, and r is the distance from the nucleus. So we would calculate that electronic wave function and its kinetic energy, again, second derivative. Then we calculate the attraction. So we sit on nucleus 1, and we loop through the attraction of the nucleus to all of the electrons in the molecule. And then we go to nucleus 2 and calculate the attraction of all the electrons, and the nucleus 3 and the attraction of all the electrons. So you can see how we just go through every piece. This is what's going on in Gaussian, and it's a shocker to me how fast it is. Right? You're doing this on your laptop, and it's, for a small molecule, it's going through all of these calculations thousands of times a second. So I and J are the electrons. So this last one is, we sit on nucleus I and calculate the repulsion to nucleus J all the way up through N. So this is the distance between the nuclei, the distance between the nucleus and the electron, and then this is the distance between the two electrons. So M is the isotopic mass of the nucleus, and little m is the mass of the electron. This upside down del squared is the partial derivative. If you're in Cartesian systems, it's with respect to x, y, and z. If you're in a spherical system, it's r, theta, and phi. And this epsilon here for Coulombic attraction, that's the permittivity of the vacuum. So that's how the Coulombic charge drops off through the vacuum of space. And then r is the pairwise differences. So the distances between each of the pairs of particles. And then z is the number of protons in the nucleus. And then e is the elementary charge. Okay, now this last term, though, is a real problem. Because think about the particle in a box. If it helps, think about that slinky, okay? That's representing the electron in the box. So what's the x position of the electron in the box? It goes from minus L/2 to L/2. And we have a wave function. But there's no x coordinate. It's a wave description of an electron, not a particle description of an electron. So this is really a classical physics model for electrons and protons. And when we get to the electron position, we have a real problem, okay? So since we're treating the electrons with wave functions, it's not real easy to calculate this Rij, okay? We can, now for the particle in a box, it's most probable to be in the middle, but in the second excited state, there's two places where it's most probable, the left-hand side or the right-hand side of the box. So again, you have to take the average position. You're gonna have to do some fiddling, all right, for this last term. And that fiddling is called the electron correlation. And that's what separates the different levels of theory. So there's a lot of different models that have this electron correlation term where we're trying to deal with the wave nature of the electron, but calculate a Coulombic repulsion and also a Coulombic attraction in this case. So that's why it's still pretty complicated. When we go to computational chemistry, we got to pick a model for this electron correlation term because it's not as easy as calculating Rij, the distance between two electrons, because those two electrons are described by waves. There's not a particular spot to calculate the distance. Does everybody see the problem? Yeah, okay. So we've come a long way from the particle in the box. This was our Hamiltonian energy operator for the particle in the box. And you can see why it was easy to do that in one dimension. You guys did it by hand, okay? You even did it in Word, okay? I forget about that one. doing that in Microsoft Word, equation editor. It's not going to happen. Okay. So this is how we select a model chemistry. Since the electron correlation cannot be solved, we have these approximates, solutions to the Hamiltonian. So these model chemistries examples that we'll go through are like molecular mechanics. This UFF stands for universal force field. I've underlined the one that I would use. Like if I were to go in and use these are all options, but I tend to use the UFF model. Semi-empirical, I just cut my teeth on Austin method 1, but some people like PM3, but I use AM1 typically. Ab initio, Hartree-Fock theory, HF, I use that one if I'm going to use an ab initio model. And then configuration interaction, I don't do a lot of those calculations, so I don't really have a preference. And then density functional theory, I use B3LYP, and that's the one I'm teaching you guys in class or in the lab. Okay. So we'll look at all 5 of these types of models. Okay. Now I'm just kind of giving you a broad overview of these. Every one of these is way complicated and beyond the scope of the course to really get into the weeds. So let's look at molecular mechanics. One way to deal with the electron correlation term is just to get rid of all the electrons, okay? And just calculate an attraction repulsion function for every pair of atoms. And so that's what it's doing. This is the Lennard-Jones 612 potential. It gets its name from this 1 over r term raised to the 6th power and the 12th power. Okay. So whenever you have a positive potential, that's repulsive. Whenever you have a negative potential, that's attractive. Okay, because think about energy. If you're going down in energy, you're going negative potential. You're going up in energy, it's positive potential. Okay. So look at the 12 factor. So it's if I get the molecules too close, okay, then I've got R in the denominator, so it gets smaller and smaller. As it gets smaller, I hit that 1 over R to the 12th power, so it goes up really steeply at small r's. But that drops off pretty quickly. And then I have this more gradual term of 1 over R to the minus 6. And so as R gets smaller, that term gets more and more negative. Okay, but it gets negative as a 1 over R to the 6th power. If you put those two functions together, you get this shape right here, where there's going to be a minimum. Now we've got a couple of factors that we can play with, the sigma and the epsilon. And the epsilon will give you the depth of that well, and the sigma will move it left and right. So this kind of gives you an equilibrium bond length, okay? And the epsilon gives you the bond energy. So for those two terms, the sigma and epsilon, we can tune the bond length and we can tune the bond energy. Hey, that's great, because I can go to my organic chemistry book and find that table that says, here's the bond lengths and bond energies for a CH bond, for a carbon-carbon single bond, or carbon-carbon double bond. So I can go and find all the different types of atoms that organic chemists have identified and all of their bond lengths, and I can put that table in the computer. And I can say, all right, let's make this molecule with the equilibrium bond length out of the organic book that has the carbon-carbon double bond, the carbon-hydrogen bond, and so on. So this is a very fast model because it just goes through the atoms and puts in the preferred bond distance. Now, what if I'm in a strained system like a cyclopropane? Well, then it won't be at its preferred bond length. It might be uphill a little bit. But I can still calculate the relative energy of that molecule. So it allows us to do all of that. So this is how it gets around the electron correlation, is by ignoring all the electrons. It's really good because it's so fast for larger systems. So if you're going to do a protein or an enzyme or something like that, this would be the model that you would use for thousands of atoms. Okay? And so this is how you select it. On that method tab, you click mechanics here, and then you pick your model, and UFF would be the model that I would choose. Okay, let's talk about semi-empirical methods. So this eliminates all the core electrons. So let's look at our periodic table. What do we mean by core electrons? Let's look at carbon. Carbon has 6 electrons, but it only has 4 valence electrons. So 2 of those electrons are core electrons. And that core would be the helium core. Okay, let's go down to arsenic. No, let's go down to germanium or tin, or even lead. Let's go down to lead. Well, the metals. Let's stick with silicon. Make it simple. Okay, I didn't want the transition metals in there. So silicon, 14 electrons, but how many valence electrons? Still only 4. What's the core for silicon? For silicon, it's neon. So this ignores all the way up to the neon core and just calculates the 4 valence electrons on silicon. So it's still able to scale up with big atoms, but only model the core electrons. So it just, and it does this without the electron correlation term. Now it uses what we call effective nuclear charges. So instead of silicon having a nuclear charge of 14, it reduces that because it says those core electrons that are essentially the neon cloud have reduced those 14 charges in the nucleus to something not quite down to only 4. You know, there's 4, if you take away the core electrons, there's only 4 electrons, but those 10 electrons have shielded the nucleus, but they haven't perfectly shielded it. Like it doesn't take away 10 of the proton charges in silicon. It might take away 9.8, or it might do really well at shielding and take away a 10.1. Okay, so these effective core potentials is what it would use for modeling silicon. And it's good for atom types that don't break the rules. Like an atom type that breaks the rules would be a cyclopropane. You've got a cyclic molecule with 60-degree angles. If you go through your Vesper shapes, there aren't any comfortable Vesper shapes with a 60-degree angle. We've got 120, 109.5, 180, maybe in an octahedral like sp3d2, you have 90-degree angles, but there's nothing with a 60-degree angle. So cyclopropane is a really strained molecule, and this is gonna have a hard time being accurate in terms of the energy of a cyclopropane. This is how you select it. You pick the semi-empirical in the model, and then you come over here and pick the individual model, PM6, AM1, all of these different options. Then we get into ab initio and density functional theory. So this requires 2 pieces. It requires a level of theory, which is how we deal with the electron correlation, and it requires a basis set. Okay, the basis set is the freedom of the electron cloud. So the theory part estimates the electron correlation, and one way to estimate it is just to set it to 0, just to ignore it. And so Hartree-Fock theories, 2 names put together, Hartree-Fock, that ignores electron correlation altogether. And these others, perturbation theory or coupled cluster methods, just have other ways to estimate that electron correlation. But the main one is Hartree-Fock, where it just ignores the electron correlation. Now, how is that valid? That's a piece of the energy of the molecule. Most of the time when we're doing Gaussian calculations, we're doing products minus reactants, maybe to find an equilibrium constant or some kind of reaction value. And if we ignore it for the products and when we ignore it for the reactants, the error cancels quite a bit. And so we can still get accurate calculations from Hartree-Fock theory because the error in the products and the error in the reactants can mostly cancel out. Then we have density functional theory, which is you would select DFT in that model area and then come over here and pick the particular model for density functional theory. Again, we go with one of the longest running ones, B3LYP. Again, this is modeling the total electron density as opposed to Hartree-Fock theory, which is dealing with individual wave functions. Again, explaining this one would be too far into the weeds for an undergraduate course. It also needs a basis set for building up the electron wave functions. And so let's talk about approximating this electron correlation term. So it's hard to, again, nail down the location of an electron because it's being modeled as a wave. So what we'll do is we'll pick the most probable location for a single electron, and then we will shield the nucleus and we'll reduce that nuclear charge. So we'll estimate that this nuclear charge is a smaller z. So we'll reduce the z on this nuclear charge here because of the smeared presence of all of this electron wave function. So we can see how the other wave functions obscure the nucleus and not have to pick a location for each electron. And so we can just reduce the nuclear charge, and that accounts for this smearing of the wave functions to shield the nucleus. So let's talk about the basis sets. These are all of our options for the basis sets. So it's a crazy mess, alphabet soup. Okay, and so this is the one that we would typically use. This one right here, this 6-31G. But as computers have gotten faster, then we're able to use some of these larger basis sets. We'll use this one for the large atoms, like iodine. When we model iodine, that's one we'll use. This STO3G is the Slater type orbitals, and it's the minimum basis set. So what are we doing when we're adding more functions to a molecule? We'll talk about that in a minute, but the very minimum basis set is the orbitals that you learned in freshman chemistry. So if we go up to silicon, let's use that one again. It's got a 1s, it's got a 2s, and a 2p, a 3s, and it's in the 3p section. So to model the electrons in silicon, we would have all of those orbitals, but no more. If we wanted to give the electrons in silicon maybe some more freedom to go at other angles, we might throw in the 3D orbitals. Now those are higher in energy than the 3p or the 3p orbitals, but they do provide some flexibility. And with Gaussian, we can only use, we can use whatever percentage of those orbitals we want. So we can mix in 10% of a d orbital and give those electrons freedom. So you don't need to know like the details of these things, but I'm just showing you how we build up the orbitals and what these numbers mean. So 6-31G means there's 6 primitive Gaussians in the core and then 2 functions in the valence electrons. And this is what we mean by building up those. Now the wave function for the electron, if we were to look at the hydrogen atom and how Schrodinger solved it, this was the wave function for the hydrogen atom. It was an e to the minus r function. And the integral of e to the minus r is not as clean as the integral and the derivative of e to the minus r squared. And so if we could use Gaussian functions, we could speed things up enormously. So that's why the software is called Gaussian, is the radial distribution of the electrons from the nuclei are using Gaussian functions. Now it's so fast that we can actually mix in multiple Gaussian functions so that we get closer to the real shape of the blue curve. And so you can see these 3 functions have been mixed together to form this green one. And this green one is a little bit more peaked in that area closer to 0. And so that's what we're doing with all of the 6-31 and 311 and all of those different numbers. It's just showing you that we're adding in more and more Gaussian functions to get closer to the right answer in terms of the wave function. Then we can put in polarization functions. So for silicon, we could add in d orbitals. Heck, we could even add in f orbitals if we wanted to. And you can see this here. We could add in d orbitals, or we could add in 2 d orbitals. So we could go to the 3ds and the 4ds and add them in. Why would we do that? Well, the electron has no understanding of what an s orbital, a p orbital, or a d orbital is. Okay? So it's totally free in space. So the more freedom we give the electron in space, the more accurate our calculation is going to be. So adding in f orbitals and d orbitals to our molecule gives that electron more space, more freedom in the angles it wants to choose in terms of how it moves and makes a molecular orbital. And it's pretty costly to do that to every atom. Maybe you want to just do it on the atoms that aren't hydrogen. Think in an organic molecule. You've got hydrogens and everything else. And so that's how this Gaussian program was built up. Anytime you have those parentheses, the first one is for the non-hydrogen atoms. They call them the heavy atoms. And then the second in that parenthesis is for the hydrogen atoms. And so whenever you're just putting a D in parentheses, you're putting D orbitals on all the carbons, oxygens, nitrogens, but you're not putting D orbitals on the hydrogens. Okay. You can if you put them, use the next drop down box and put a D on there too. A lot of times we put P orbitals on hydrogens. That helps with hydrogen bonding. It's a more directional orbital. So we can put P orbitals on hydrogen and get more accurate hydrogen bond calculations. So the more freedom you have, the better your energies. Diffuse functions. Let's say we have a negatively charged molecule. Electrons repel each other. So if we've got more electrons than protons, that cloud is going to expand. And so that's what diffuse functions mean. So we could put them on just the heavy atoms with the single plus. If we put double plus, we put them on all the atoms. So we're letting the molecule's electron cloud expand a little bit. And it's like we're adding in s orbitals. So we could add p and d orbitals in through the diffusion, polarizability functions. We could add in s orbitals. So if we did a plus on silicon, it would be like adding a 4s orbital for silicon. So it's good for anions and also for transition states. So this monster basis set for really good energies, it's got all kinds of Gaussians built into the core and in the valence electrons. This one has diffuse functions on the heavy atoms and on hydrogens. And it's got 3 D and F functions on all of the heavy atoms and 3 P and D functions on the hydrogen atoms. So that electron cloud is completely free to go at any angle it wants. And the only downside is this is going to take the computer a lot longer to calculate. If you put that basis set in on your laptop, your battery is going to die before the calculation is over. Okay, so better plug it in. So this is the sort of a guide for the basis functions that we would use. If you've got a huge system, 200 to 2,000 atoms, you're going to be using molecular mechanics. So you don't need to pick a basis function. If you're going to try to do density functional theory or Hartree-Fock theory, you've got anions, you want to use the pluses. You have strained rings or whatever, you're going to need polarizability functions. The latest edition of this computational chemistry book written by Forsman suggests this because he says computers are fast enough now to handle this, but not our computers. So if you're going to use it in the laptops and so on, you probably don't want to use this one. Just go with what we have suggested in the lab and it'll be really fast. I call those calculations that we're doing while you wait, right? You type it in and you hit go and you can sit there and wait it out. If you use the one that Forsman suggests, you're going to have to go home and come back. Okay, so it's not a while you wait calculation. So these model chemistries have the level of theory and basis set. We just finished talking about both of those. So these are the different molecular mechanics keywords like UFF, AM1, and so on for semi-empirical. Ab initio and DFT have these pairs, and so this is the one that we're using right here, the B3LYP/6-31GD. So now you know a little bit more. This first part is the level of theory. This second part is the basis set, the freedom of the electrons. Okay. So this is your selection guide. Again, polymers, all kinds of larger systems, UFF or AM1, medium systems, you want to use B3LYP, anions and transition states, you want to have this plus in here to give it diffuse functions. And then combinations. Let's say you're doing a porphyrin ring and you want to model the iron center and you want to really get an accurate calculation of the iron and its interaction, say, with oxygen or carbonyl or something like that. You want to use a high level of theory for that important interaction, but you don't want a high level theory for all these arms and stuff out on the porphyrin ring. Those aren't going to affect the chemistry very much. So you can use molecular mechanics on those and use ab initio or DFT for the iron interaction. And that's called a ONIOM or MMQM. So molecular mechanics, quantum mechanics system. And they won the Nobel Prize for that in the software. So that's computational chemistry won a Nobel Prize in being able to set up different types of calculations in one molecule by setting different layers. and being able to merge those results. So why not just go with the most complete basis set and the highest level of theory? If we could do that, we would get to the true solution of the Schrodinger equation. We'd have a wave function that was truly free, and we'd be able to model the Hamiltonian really well, the electron correlation term, but the calculation time goes to infinity for that. So we've got a problem. We can go high in the basis set and low in theory, and we can go high in theory and low in basis set, and then we can kind of estimate this region in the middle. So that's I guess an overview of how to choose your model and what kinds of models. Let's look at now what Gaussian's doing for our molecules. So we're going to do a job type of optimization and frequency calculation, because we want to model the vibrational frequencies of our molecules, because that's part of this course, is to study the vibrational structure and vibrational spectrum. You could also simulate the NMR spectrum and all kinds of other things. So the title tab, you can put whatever you want in this. I would just avoid using these special characters. This link 0 thing contains all the molecular orbital data. It picks a checkpoint file. If you're going to use the molecular orbital editor, you need to use the checkpoint file that's designated in this link tab. Let's talk about computational time. So triamino trinitrobenzene, TATB, is a nice calculation. It has a clean number of basis functions, 300 basis functions. You do a HF calculation on it. And so this molecule has been calculated going way back. So the very first implementation of a Gaussian type program was on this polyatom supercomputer in 1967. Okay? And this calculation took over several months on that machine. Then we get to Gaussian 80 on a VAX. It took a week. On this, again, a VAX supercomputer. Gaussian 88 on a Cray supercomputer, it took 1 hour. And Gaussian 92 on a Cray supercomputer, it took 9 minutes. And then I started studying this molecule. And so with Gaussian 92 on my super hot 486DX double chip, I took 20 hours. Okay, so this is my calculation, 20 hours. Then I got an upgrade. I got to a Pentium 90. In Gaussian 94, it took 2.6 hours. Gaussian 98 on a Pentium 3, 500 megahertz machine. So 500 megahertz. Okay, 24 minutes. Okay, that's pretty good. And then a 3 gigahertz machine, unheard of. Okay, Pentium 4, a Gaussian 03, less than 5 minutes. So that's pretty cool, the speed up. Okay, now this kind of breaks your brain. It's almost like a Doctor Who thing. I did a calculation on this machine of a pretty large polymer fragment, and it took 2 weeks of CPU time. So it sat there plugged in doing this calculation for 2 weeks. Okay, we finally got the result. Great. If I take this same sort of chart of times and I extrapolate backwards to 1967, how long would it take? Huh?
A year.
A year? Okay. What else? What do you think? Decades? 1,500 years. Isn't that crazy? So if that's how we've sped up, that's how fast computational chemistry has gotten. You know, what would have been impossible in 1967, I mean, that's an impossible calculation. And this is a small molecule. It's 3 aminos and 3 nitros on a benzene ring. And so impossible for the Cray or the CDC 1604. But we can do this in 2 weeks now, probably even faster. I haven't done the calculation again. I need to. And we're at Gaussian 16. So this is what it's doing. This is the last slide here. We input the nuclear coordinates, calculate the energy, calculate the gradient, and see if we're at a minimum. If we're not, we move the geometry. And then if we are at a minimum, we do the frequency calculation. So it's 2 different calculations. The top piece is the geometry optimization, and then we get to the frequency calculation. This idea of negative frequencies is just sometimes you're at the top. So like if a bond is stretching or bending, you might be at the top of a potential energy surface and not at a minimum. If you're at the top whereas the root, it's below, so it's a negative frequency, and so we call those imaginary frequencies. So we would reduce that symmetry, go back into the geometry optimization calculation, and then once we have no imaginary or negative frequencies, we have the optimized geometry and energy data, and then we can go in and simulate the infrared spectrum or the Raman spectrum. The rest of this is just post-calculation options. We could simulate spectra, we could calculate molecular orbitals, we could do electron density surfaces and electrostatic potential maps. And some of these are on the homework. Basically, this is the MOs that we've been dealing with. This is the electron density. You can sort of look at the 95% or 99% density in the cloud shape. And then this is the electrostatic potential map, where I was talking about how the electron cloud shields the nuclei. So the electron cloud in a benzene ring is all above and below the ring. And so if I'm walking along there with a positive charge, it feels attraction to the negative charge. If I'm walking out here around the hydrogens, the electron cloud's been pulled into the ring, so the hydrogens are exposed. And so I feel a positive charge where the hydrogens are. This is really great. I wish I had taken PChem before organic, because this explains where an electrophile is going to go and explains where a nucleophile is going to go. Because an electrophile is going to attack the ring where the electrons are, and a nucleophile is going to attack the side where the hydrogens are. And so understanding the electron cloud would have made organic chemistry so much easier. But I can't convince them to put this in after Chem 2 and teach PChem first and then organic. But I always wanted to try, like take a cohort of students through this course and then send them into organic. I bet they would be the best organic chemists ever, you know. So anyway, that's something that maybe they'll let me do one day. Y'all have a good day.